shocks. Slightly different one. So what we've got here is the flow coming along, and it's actually bounded, so it's actually within an engine. We've got a little ramp here of theta, and it's caused a shock wave. Because it's contained, this time it's bounced, or reflected if you like. So what we've had is it comes along in region 1, straight, and it gets deflected. What by? By theta. So in other words, all of these now, these molecules are going at an angle to the horizontal of theta because that's the wedge. Now the problem comes is if we up here, you can see that if we're not careful, these are going to go splat into a wall, and that's not going to happen. So as a result, this gets compressed and this shock actually forms as a result. The question is, what is actually this actual angle? We've put it as phi, but I'd like to know more likely what is it in terms of the shockwave angle beta. So this is what you've got to think. So we've actually got theta, which creates a shockwave. Now up here, this Mach number is different. So therefore, it will create, if you like, it's not the same Mach number as region 1. Now tell me, in going from region 2 to region 3, the flow has to turn around how many degrees? Not so easy this one, but it started off horizontal and we actually made it go through theta. I want it back to the horizontal. What does it have to turn back towards? Theta. So we've raised it by theta and we've got to bring it down by theta. So how would you calculate this? Well, what you would do is you'd use, remember for calculating shock angle betas, we need to know the wedge angle theta and the Mach number. So we start off with the Mach number in the first region. We use theta, we use the old diagram here, and that gives us a beta value. You can see it here. And if we then work our way through, like in the tutorials, in the second region, the Mach number will have changed. It will have gone down. So how do I actually find beta in the next one? Well, all I do is I take that Mach number, and the first thing I do is I say, right, I know that it's changed by theta, so I look at theta again as a deflection angle, but this time I look on a different curve, the one related to region 2's Mach number, not region 1. And then I read off what the shock angle is beta. So, how's beta? Beta's measured, you can see, from the direction of the original flow. So this beta was measured from the horizontal because Mach 1, or the Mach number in region 1, was coming from the horizontal. This one is measured from the direction that we were going for here and comes down. So that angle from the dot or dash 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 down to the reflected shock wave is basically beta 2, if you like, the angle from there. So what that means is that, if I'm right, let's see, beta 2 would equal theta plus this part from the horizontal down, which is the same angle as phi. So the angle that we can get out of that gives us the shock wave angle from the reflected, and that equals theta, which we already know. Take that away, and then that would give us the angle that we would draw that reflected shock at, if you weren't using a computer. Okay, so that means that if you know how to operate this, you know how to do reflecting shocks as well. Right, so what would happen if the shock was generated for a free stream Mach number and it's just about able to produce one of these oblique shocks? It's just getting in there. It's not quite missing the curve, but it's just about the limit. If we actually bring the Mach number down a bit more, there, what's going to actually happen to that reflected shock? Because we're just about winning as far as the shock concerns. What actually happens is that you can see it actually doesn't quite make it all the way up, and it forms a standing shock, becomes normal to the surface. So you can get quite complicated shock behaviour inside engines if you're not careful with making sure that you've got the shape and the ramps and the speed right. We don't want standing shocks because they rob us of a lot of energy. Remember, on the other side of a standing shock it would be subsonic, whereas on the other side of this one it would be supersonic. Okay, so it can get more complicated. No, you're not going to be calculating these, but it's good to be able to understand them. So what we've got is we've got a duct probably inside an engine. The flow's happily coming along horizontal, so far so good. But we're deciding, if you like, to close this amount of area down. So what we've done here is we've lifted it up by θ1, and we've got θ2. Now, if θ1 and θ2 were exactly the same angle, then all the shocks would be symmetric all the way along. And you wouldn't see this dashed line called a slip line there. So basically this one would be the same strength as that one, this one be the same strength as that one. But they're not equal. So what happens is the higher wedge angle creates the stronger shock and gets further, if you like, before it's actually hit by this one, which is a proper shock, but it's not quite as strong because the wedge angle at the top is not as big as at the bottom. So now we've got a bit of asymmetry coming in, and you can see when the two shock waves hit, they produce two other shock waves which are not in the same direction as before. And what's interesting is that there is a region basically down the middle between these two. And what you find is that the speeds are different on either side, but the pressure is the same in this region. So pressure 4 and 4 dashed are the same, but the speed in region 4 is a different speed from region 4 dashed. So that discrepancy, that difference in the sort of one, what looks like one region but is in fact two, that's called a slip line. And it's the reason because the two sides of this particular duct were not equal. Okay, so they're incident shocks, they intersect at E, reflected shocks C and D are the result. If the upper and lower ramps were the same angle, no slip line appears. Because ramp 1 is at a higher, then shock A is stronger than shock B. Therefore, the streamline passing through A and C changes its entropy differently. In fact, it would be a higher entropy change to the streamline passing through B and D. So as a result, different types of entropy, this breaks into two. The dashed line is the slip line, the pressure is the same on either side, the velocity direction is the same, but the actual values of the speed and also, for that matter, the temperature and the density are different. Okay. Now, let's say that we have an engine and it's got a nozzle, and that nozzle is giving flow out into the free stream. What we really want is for it to be nice and straight flow and no shock waves either inside or outside. So this one's not doing so well. This is not being operated at the conditions that it was really designed for, and that's probably because it's a fixed nozzle and maybe it's going up through the atmosphere, the altitude's changing, the pressure outside is changing, and so the way that influences the behaviour here is different. So what happens with anything which is a sort of a duct or a nozzle coming out is that you end up with this dotted surface here, which is a constant pressure, and you can see this thing here as well. And it's interesting because if you've got an expansion fan that hits this constant pressure region coming from as a result of the nozzle, it has to maintain on this surface the constant pressure, and as it rebounds back it forms a shock. So what happens if it was a shock wave? You can see here we've got a shock wave here and a shock wave here leaving that particular nozzle. Unfortunately, they hit each other and then they basically have two shocks up here and down here as a result, and they both hit that constant pressure surface. When they rebound, the shock rebounds as an expansion fan. So if it's expansion fan hits, it produces a shock down, and if it's a shock up, it produces an expansion wave down. Or an expansion fan down is probably better to call it. Right, so boundary layers. As you are now quite used to boundary layers, you've been doing calculations on them. So boundary layers grow as they go along the surface. What happens if they get hit by a shock wave? Nasty stuff, this. So you've got a poor old boundary layer here growing from left to right. And it gets hit by a shock wave coming down. Now what's the shock wave going to do? It's going to heat up the boundary layer. What happens to the air in the top of the boundary layer is it's going to get hot, and that's going to go into the boundary layer, and the boundary layer is going to swell. And what's happening here is that it's even separated from the surface. But the problem is, when it swells up in the region it swells up here, it's creating a kink in a supersonic flow, which creates a shock wave. And that wasn't a shock wave that we actually had there originally. Where's that top one coming from? Probably the lip of the intake of the actual engine duct. This one's coming in here. So what happens is this one grows because the boundary layer's got heated and swollen up. So now we've got an extra shock wave which hits ours. That gives us two other shock waves going along here, and off they go. Now as this goes up, you can see the heating effect is only going to affect a certain amount, and then it goes down. Well, of course, this is giving space more and more. So what's actually happening here is we're getting the point of expansion. And when we get down here, we're compressing again. Suddenly it's gone to the bottom, and so what happens is, guess what? All of this bunches up, and we get shockwave, and that's going to hit up there. So particularly in supersonic wind tunnels, you've got something that you are investigating, and the shocks go off, hit the tunnel walls, and you get this effect further down. So this could be the tunnel wall of the supersonic flow at the top, and also at the bottom and the sides. So it gets very, very, very messy in supersonic tunnel as you go after the event. But because supersonic flow is not affected from, if you like, downstream or upstream, therefore once the flow has gone past our vehicle, it doesn't matter how bad it gets really, we will have the value that we want on our actual vehicle. But if it's going inside an engine, and this is happening, this is actually a problem. You can see a sort of a better one here. Here's the intake. It's produced, it's sort of a tip like a ramjet. In it comes, the dotted line's the boundary layer. Same thing as before. This one actually hits the top, and now it's gone inside. So that tells me that the part under C is subsonic flow. The part between B and C was actually supersonic flow in this boundary layer. So it's obviously quite a strong case. Boundary layers obviously always have some subsonic flow in them. They don't usually have supersonic flow, but they can do. So there's my subsonic flow under C. So that would have been like a sonic point there. The energy from the shock wave goes up. It swells up more in the boundary layer than it would have normally. You can see what it was supposed to be was more like along here, meeting this part here. So all of this part now is swollen up. And as we said before, what happens is this is now making it difficult. So it's beginning to produce lines which come together to form another shock. This then causes a shock interaction, which will alter them a little bit more. In here, this is a different speed inside this boundary layer, and so therefore we have a different effect coming through, which also produces a shock wave. As we go over the top, and a molecule then gets more space, it expands, then we get expansion waves. When we get to the bottom and it goes back to normal, it goes back to a shock again. So if we don't have a boundary layer in, we would have one shock which bounced off the surface to two. Instead we've got 1, 2, 3, 4 shocks at least. So boundary layers and supersonic shocks do not work well together, and it's a complicated area. But once you understand where they're going to actually appear, then the shock waves are at least predictable, if not difficult to calculate.